Really, what I'm going to talk about is design of UHPC structures. So structural design guidance is certainly an important part of that, but design of UHPC structures is really what we're aiming for. How can we get to the point where we are designing UHPC structures? So as Steve mentioned, I have a long history in this topic area, and I'm also the chair of ACI 239, the UHPC committee. So I'm glad to be here talking to you today about this. I do work for the US federal government, so I got to show my disclaimer. I'm not endorsing anything. UHPC is a class of materials, and I'm here talking about that class of materials. So a path forward towards structural design or design of UHPC structures, as I said. So probably 5-6 years ago, there started to be a groundswell of interest in this topic. How can we start using UHPC to address some challenges we have in structures? How can we build structures using this new class, new structural material? And with my experience in this, I started thinking about how we can get there, how we can, what do we need? What does the path look like? And I recognized two things were definitely needed. One was some formal design guidance that people could use, because when you're designing structures, you can't just sort of do it willy-nilly. It's a pretty formalized process. There needs to be guidance for the people who complete that process. But we also needed a test method. One of the unique things about UHPC is how it behaves in tension. And you can get some significant advantages from that in your structural design. But what are those properties? If someone tells you they have a UHPC, and you don't really know, if you don't have a standardized test through which to define the properties, how do you handle that? Where do you go if you're trying to do a structural design? How do you get a vendor to build you a structure that meets your design? So I knew that we needed both of those things. And so the path is becoming much more clear. We knew we needed these things, and we don't just need them. I have copies here of these two things. These are real things that over the past few years have been developed. And so it's not just an emerging area, it's something that is really coming to fruition. And pretty soon we're going to see more of this structural design using UHPC. So we're talking about UHPC, a little bit of eye candy there. That's a pretension girder that looks kind of like a normal pretension girder, but looks a little different too, different than at least what you might see for a conventional concrete solution on that. So what's our goal? What are we aiming for? Well, we're trying to get to the point where structural design with UHPC is something that might be commonplace, where appropriate, when the solution sort of fits the need, maybe UHPC works well. So the goal is to get there. What might that look like? So, we could be talking about many different things, but since I work in the highway sector, I'm going to talk about prestressed girders for a moment. So with UHPC, you can do things a little different than what you do with conventional concrete. So with UHPC, from an engineering standpoint, you might get a longer span length using UHPC, and that could give you some advantages. Your cross-section might be a little more slender, as you can see there, so decreased dead load. You might have a more durable structure, and that might be something that you really want. So there are some engineering benefits. Just in general, maybe it lets you accelerate your construction. Maybe you can span all the way across your waterway, so you don't need to have some piers in the water. Reduced local environmental footprint, less maintenance. There's a lot of advantages. So in your particular project, you might say, okay, this is worth it to me. UHPCs, we all know they're a little more expensive, but that's the material cost. When you actually look at the full structural solution or the full construction cost, there are some benefits that you can get. So just to give you a sense of the kind of things people are thinking about, why we might want to go in the direction of using UHPC. So we sort of have a sense of what that goal is, but I want to digress for just a second and talk about how we get there. How are we going to achieve this goal? So expertise is certainly a big part of that. And the UHPC community in the US and around the world has been sort of a tight-knit group. And there's experts who know about UHPC, and they're starting to bring that to bear. And the community is getting bigger, and that's great. The community is growing. Lots more people are bringing their voices into the discussion, and that's great. But it's not just about the expertise. We need more than just the expertise. We also need to collaborate, and we need to build on the work of the people that have come before us. We need to have some perspective. This is not the first structural material out there. People have thought through a lot of things like reliability, like what level of ductility is required in your structure. Those sorts of things, we need to build on what's already been done, and we need to work together towards appropriate solutions, towards safe solutions where UHPC can start to be used in those structures. So it's not just about the expertise. It's really about all of us working together to rise the tide, to raise all boats. So structural design guidance for UHPC. The concept is that UHPC is a structural material, provides certain advantages, and we can use those in design and construction. Now, how do we get to actually having structural design guidance? So we need some knowledge about how UHPC behaves at the material level. So what are the basic engineering properties of this structural material? That's just the beginning, though. We need to take those properties and we need to start building structural elements. And we need to say, okay, how do those material behaviors translate when you're looking at it at the structural level? So we need to understand that too. You need to understand both of those things. And then if you really think about structural design, what we have in structural design is we build models. We have a model of how a material behaves. We do that at the material level. We take it up to the structural level. We combine all that together and we create a process for designing structures that are safe. So we need to do all that for UHPC, just like we already have it for structural steel. We have it for reinforced concrete. This is sort of a new kind of concrete. It behaves differently. So how do we do that? So a couple big questions, though, down at the bottom, and it's really the same question written two different ways. Can we just assume that UHPC is conventional concrete with benefits? Is it that simple? Can we just say it's conventional concrete with a few tweaks, it's got some extra benefits to it, let's just charge forward? Or, maybe a little more sophisticated way to say that is, can we assume the same assumptions that we use with conventional concrete hold for UHPC? Just maybe tweak them a little bit on the edges. That seems like a real simple path forward. We already have guidance for conventional concrete. Maybe we can just use it for UHPC. Now, you could probably guess I'm asking the question because I got an answer, and I don't think the answer is it's quite that simple. So let's talk about assumptions for a minute. These aren't all the assumptions that go with conventional concrete, but some of the assumptions we deal with in conventional concrete. Engineering mechanics is fundamental. Sure, that's all good. We can sort of ignore the post-cracking behaviors usually when we're dealing with reinforced conventional concretes. Creep, we sort of have a sense of how that behaves, but it's through a lot of empirical data, okay? Flexure, when you're dealing with a flexural element, you've got two limit states that you're most concerned about. That's your compression crushing and your tensile reinforcement yielding and rupturing. And then finally in shear, the limit states dependent on reinforcement yield and aggregate interlock in shear, in a beam shear type behavior. So we're sort of familiar with all of that for conventional concrete. So what's that look like when you're dealing with UHPC? Well, engineering mechanics is still fundamental, that's for sure. But UHPC behaves differently in tension. So now in tension, we've got post-cracking tensile resistance. It's a major benefit, but it also changes the member response. So there's a big difference there. We can't just adopt conventional concrete concepts when we're dealing with the tension side of the behavior. Creep. Well, creep's still empirical. We still need data for creep. And unfortunately with UHPC, we don't have as much data yet as we have for conventional concrete. That's sort of obvious. It's a new material, new class of materials. So it will come with time, but our knowledge of creep, our ability to predict exact creep behaviors is a little stunted right now, but we'll get there. Flexure. Flexure, you can see there I've listed 3 different limit states, not just 2. That's important. We can't forget that third one. UHPC has tensile resistance post-cracking, but it also has a tensile limit. And when it gets to that limit, the fibers start to pull out of the matrix and you get what's called localization. So that sounds like, let's talk about that a little more. So the tensile localization of UHPC, it happens somewhere around 3,000–4,000 microstrain. And if you think back to just as an example, mild steel reinforcement, what is the yield strain of mild steel reinforcement? Depends on what your grade of reinforcement is, but it might be 2,000, 3,000 microstrain, something like that. So around the same point when your steel starts to yield, if you're dealing with a reinforced concrete structure and you don't have any pre-stressing or anything like that, you might see this limit state get reached in the UHPC. So now that might be something you need to think about in your design. And the last one I'll mention, there's the shear limit state. In UHPC, it's a little different. Because we have this strain limit in the UHPC, the shear behavior is a little different. We're not just dependent largely on the yielding of the stirrups in your beam. You might not even reach yield in the stirrups in your beam before your UHPC reaches its strain limit. So there are some differences in behavior. So I think maybe I've hopefully begun to make the point that you can't just adopt conventional concrete philosophies wholesale. UHPC is a little different. All right, so I'm going to digress. And I mentioned there were two things. There was the design guidance and there was that test method. So now let's talk about this test method for a minute. So what I'm showing here on the screen, and this is probably a better picture, is a stick of UHPC being pulled in tension. So if you want to know what the tensile properties are of a structural material, a great way to do that is to pull the structural material in tension. It allows you to in a very straightforward fashion, you get the stress and the strain. And as an engineer doing structural design, you want the stress strain response of the material. You want to know that. So here's some pictures there on the left showing some testing machines pulling sticks of UHPC. On the right, that's the specimen after failure. And you can see lots of those little tiny tight cracks and then eventually localization cracks. So that's when it reached that strain limit and started to pull apart. The tensile response of a UHPC, this is just an example of one particular test we ran. And you can see that you have this elastic behavior. You get to cracking, the fibers bridge the crack, you get more and more and more cracking until eventually you get to that point that says localization. And that's where one crack starts to dominate. The fibers start to pull out and it ceases to be a straining behavior and it starts to be more of a crack opening behavior. From a structural design standpoint, my opinion is once you get into that crack opening behavior, that's not where you want to be. We want to deal with the things that happened before that, when it's straining, when it's a stress strain response, like a structural material. So this test method, it exists. It has been fully validated by AASHTO. My group started developing this about a decade ago, but about a year and a half ago, we started working directly with AASHTO's Committee on Materials and worked with their hardened concrete committee. And they balloted this last fall. The full comp balloted this in November. So it's done. It's here, but you can't quite get it yet, unfortunately, unless you contact me. I give you a draft copy of what they balloted. AASHTO will release it this summer when they release all the things that they balloted last fall. So sometime around July or so, this will be available for everyone to start using. I'd be happy to talk to people about it. Anybody who wants to start using this. Let's see. All right, so back to the guidance. So I mentioned the guidance was something that is also been drafted. I've got a copy of it here. So my group's been working with AASHTO's bridge committee, the Structural Concrete Design Committee, AASHTO T10. They have a strong interest in this topic. They want to start facilitating the use of UHPC in structural design of bridges in the US. So my group sort of raised our hand. We said, okay, we'll help you get there. Let's work together to get this done. So last June, we delivered to them draft guidance that they could choose to adopt. And we've been working with them since then on a process of sort of tweaking little parts and helping them understand where we're going and, you know, back and forth sort of thing that happens in that sort of collaborative environment. So a few details on this guidance that we developed. It's a standalone document. It's about 70 pages long, but it parallels Section 5 of the AASHTO LRFD Bridge Design Specification. Section 5 is the part that tells you how to design reinforced concrete structures, pre-stressed concrete structures. We basically said, okay, people are familiar with that. Let's build something that parallels that. And for places where there's really no difference between the two materials, we said, just use what's already in Section 5. But for something that was different, and there are quite a few things that are different, it's in the document, in this 70-page long document. Uses a 2-column format. You have the guidance on the left side and the commentary on the right side. And it basically tells you how to design with UHPC. What is UHPC? That is an important part. We had to draw the box. What is the scope of what we're dealing with? That's in section 1.1. So we define what is sort of in and what is not in there with those bullets. So it's an 18 KSI compressive strength. You need sustained tensile resistance of at least 750 PSI. And you need to have at least a localization strain that is at least as large as 0.0025. Also, there's a couple of limitations. We designed this for sort of, I guess, maybe the simpler design stuff. So we haven't yet dealt with, say, post-tension systems. And we haven't yet dealt with seismic systems. It's not to say the guidance doesn't work. It's just to say it wasn't designed or developed with an eye towards use in seismic regions or in post-tension systems. All right, finish off real quick here, just giving you a brief glimpse into some of the concepts that are in the guidance. And it, as I mentioned at the beginning, it's built on models. This is how we develop structural design guidance. We have models for the material behavior. We take those models into the structural scale. So on the tension side, we run the test, the standard AASHTO test. T397 is its number. You get the test result, you turn that into a model over there on the far right. The lower one is the one that would most often be used. It's an elastic plastic model. So you get the engineering parameters from the test, you build the model, you take that model, and then you apply it into your structural behaviors, into something like this. So if you're dealing with flexure, flexure is still flexure, Bernoulli is still Bernoulli. You've got a neutral axis, you've got the above the neutral axis compression, the below the neutral axis tension, and you apply the stress strain responses of the materials. So if your beam is made of UHPC, you've got UHPC above and below, and you're going to put the stress strain, the model of the stress strain response in tension and compression onto the cross section, and you're also going to have your reinforcement there. We're suggesting you need to use strain compatibility because it's not quite as simple as with conventional concrete, where on the tension side you have a tensile material with an enormous strain capacity that is basically flat and yielding like mild steel reinforcement. When you combine these things together, it gets a little more complicated. It's still the same analysis. It's just not quite as closed formy, if that's a word, and it's definitely not. That is important. And the other thing is the failure modes. As I mentioned, the crack localization, that is an important consideration. And if you go beyond that, you could run into some problems. What we've seen just in a nutshell is, we've seen this on large scale tests. If you get past crack localization, you can get what's kind of best described as a hinge in your structure. So you can have a very large curvature happening at the location where localization happened within your flexural element. And you probably don't want to be there unless you've detailed it for hinging. And usually we haven't detailed. That's something we do in seismic regions at the bottom of piers, but it's not something we do in the middle of our beams in a bridge. And then the last model I'll talk about is the shear model. And this is, for those familiar with AASHTO, we use the modified compression field theory for conventional concrete. We basically took that and we re-derived it using UHPC. And it actually becomes a little less empirical, interestingly enough. In conventional concrete, we have aggregate interlock, and that's an empirical approximation of the resistance you get from the concrete along a crack and shear. In UHPC, we don't really have aggregate interlock. What we have is the UHPC offering tensile resistance perpendicular to the crack. So it's trying to resist the shear. And so you use superposition. You add the resistance from the UHPC to the resistance you get from your shear steel, and you determine your capacity. It's sort of that simple. And in the guidance, we don't make you rederive modified compression field theory. We provide it to you so that you can use the equations to calculate what your theta is going to be, and your stress in your steel and all that. So with that, we really do have that path. It's starting to become clear, so we can do that design of UHPC structures. Our structural design framework, it incorporates those mechanical properties, those mechanical, the properties into models. We build those models in sort of a first principles type framework to carry it towards structural design. It's validated against experimental tests that we have done and tests that have been done by others around the world. The work has been peer reviewed for those who might be interested in that. We have published, I think, 7 different peer reviewed papers within the past year. We also have made sure that they are open access so people can easily access them. So, you can search them up online or reach out to me and you can find them. Go to my ResearchGate site and you'll see them all there. And T10 is considering it. Their goal in this process, and we'll see if we get there, but their goal is that by next summer of 2023, they hope to be balloting a guide spec on structural design of UHPC. So with that, I thank you for your attention. Thank you for your time. And I encourage you all to work together towards this kind of solution. Thank you.
I hear a lot of talk about reducing fiber content down to like 1.5%.
Yeah.
Maybe lower.
Yeah.
Any personal opinions on for major structural elements?
I'll give you some thoughts. So what the way we look at it, you need to your material, the material that is proposed to be used, needs to provide the engineering properties that you care about. If someone can develop a UHPC class material and they can use 1% fiber, I'm not saying it can be done, but if it could be done and it provided you the tensile response that you cared about,
would likely be strain hardening.
it needs,
in many cases.
it needs to be. I mean, if you're going to use the guidance that we have developed, it needs to be strain hardening. It needs to have at least 750 PSI of sustained strength, and it needs to have a localization strain that's at least 2,500 microstrain. If you can't do that, then you're outside the box. I'm not saying it's bad, but you're outside the box and you're going to have to go a different path. So I think it very well may be possible to optimize the mixed designs of UHPCs while still getting the properties. Presumably people would be doing that so that they can reduce the cost. Fibers are a very expensive part of the cost.
Yeah.
Steve and Benjamin, if I may, we had two short questions come in. The first one is how to design columns using ultra high performance concrete. How do we design the columns?
Well, it's in the guidance that we've proposed to AASHTO. You use the same basic concepts that are used for reinforced concrete. The compression side is pretty straightforward. The tension side gets a little more complicated because you're dealing with compression and flexure at the same time, and potentially shear. I don't know that in 30 seconds I can.
You can do it.
And I will put you on the spot and give you another 30 seconds. The second part of the question is how do we construct PMM curves for the ultra high performance concrete?
Yeah, it's the same sort of thing. I mean, you're designing, and you look at the flexural design, you look at the axial design, and you develop it. You step through the process is not going to be any different as what you have with conventional concrete. It's just you have to be careful about the limit states. You have to make sure you're considering all the different limit states and the stress strain response of the material.
Yeah, absolutely. And I'm so sorry, but we have time for two more questions or no?
We have time for one more.
All right, I'm going to pick one here. Okay.
There's actually.
It says, what are the? Go ahead.
We got to be democratic here. We've got to
Hi, my name is Yash, and I'm a PhD student from Cleveland State University. I'm also working on UHPC. It may not be relevant to this structural designing part. Like I'm working towards the material side of it. So you have been working and you have published a lot of papers on UHPC, but we all know that it is a noble product, right? Where do you think it is lacking, like the wider application? We just we just use it as shear key designs for bridges and everything. We can save a lot of money with it. We can do a lot of things. We can do like reduce the size, section sizes and everything. Where do you think we are lacking in promoting this product?
In promoting it, lacking in promoting? Yeah. No, I mean, I think it's getting a lot of play. I mean, you look, there's an awful lot going on here at ACI. The community is growing. The amount of vendors in the US, the people who can produce UHPC, it's growing, I think, at a very appropriate pace. As new opportunities come along, the community gets excited about that new thing. So it was connections for a while, and then it became rehab sorts of solutions for a while, and now we're moving towards structural design. So I'm not sure I'd say that it is really lacking. We have to come in with eyes wide open to know what the material can and can't do. It's not all good. Some people first become familiar with it, they think it's all benefits and there's no problems. There are some challenges with it, but it has some promising opportunities.